Hello, and welcome to this very brief presentation related to sinusoidal forms. We're going to consider waveforms of the form y is equal to a multiplied by the sine of omega t plus or minus alpha, although in this particular presentation the alpha will actually be 0. There is a separate presentation related to sinusoidal forms where the solutions are performed analytically, but in this particular presentation we're going to consider graphical solutions only. So we are going to be given a trace of a sinusoidal waveform, typical waveform shown here. And by inspection of the waveform, we are going to find the amplitude, A, in our equation. And we're going to calculate the angular frequency, the omega, within our equation. We will then write the equation in the format of y is equal to a sine omega t. Here's a brief recap of basic terminology and symbols associated with general sinusoidal forms. These are described in more detail in the separate presentation relating to analytical solutions. Firstly, symbol A relates to the amplitude of the waveform, that's the maximum height of the waveform. So if the waveform is associated with a voltage, then the units will be volts. If the waveform is associated with a current, then the units will be amps. If the waveform is associated with velocity, then the units of A would be meters per second. The lowercase omega, Greek symbol there, relates to angular velocity or angular frequency. We often use the term angular velocity in mechanical engineering, but we can also term this angular frequency in electrical engineering. The formula for angular velocity is 2 pi f, where f is the frequency. The unit for angular velocity is radians per second, rads per second. The frequency, lowercase f, and the formula for frequency is the angular velocity, omega, divided by 2 pi. The unit of frequency is the hertz, in other words, cycles per second. Short form is Hz. Capital T is periodic time. That's defined as the time it takes to do one revolution or one oscillation of the waveform, and that's defined as 2 pi divided by the angular frequency, or omega. Notice that the frequency is the reciprocal of periodic time, and the periodic time is reciprocal of frequency. The unit of periodic time is the second, symbol S. And finally, symbol alpha is the angle of the lag or lead of the waveform, but as mentioned previously, in this particular presentation the angle alpha value will be 0. For reference, alpha has a unit of radians. Just a note on amplitude, A, that's the maximum height of the waveform shown here. This is the amplitude of the sinusoidal waveform. So for example, for the function y is equal to 4 multiplied by the sine of A, the amplitude is 4. So in this case, the waveform oscillates between positive and negative 4. The following slide shows a typical solution that we'll be reviewing in this short presentation. Here's example 1b. We're given a sketch shown below of an oscilloscope trace. For the waveform shown, we're asked to determine the amplitude, labelled A, the periodic time, capital T, and the angular frequency, omega. We're also asked to state the equation of the waveform in the form y is equal to A multiplied by the sine of omega t. So from the given waveform, we're going to find the amplitude by inspection of the waveform. So the amplitude relates to the maximum height of the waveform, which appears to be here at a value of 2. So the amplitude in this particular case is positive 2. In other words, the waveform has a height of positive 2 and the depth here of negative 2. It oscillates between positive and negative 2. We should say that that's an estimate. We don't actually know if it's 2.01 or if it's 1.975, but that's one of the problems with the graphical method. We have to make assumptions, and it looks like it's 2 by inspection. Next we're going to find the periodic time, capital T, and don't forget that's the time it takes to do one complete oscillation or one complete cycle. So from the sketch shown, this would be one complete cycle, and we can see that the periodic time is 30 seconds. So by inspection again, 30 seconds is the periodic time. Now noting that the periodic time, capital T, is equal to 2 pi divided by omega, the angular frequency in this case, we can rearrange the equation to find angular frequency. So multiplying both sides of this equation here by omega and dividing both sides by capital T, we can rearrange the equation to find the angular frequency, omega, is equal to 2 pi divided by the periodic time t. Putting the values into the equation, then 2 pi divided by the periodic time, which is 30 seconds, produces an omega value of pi divided by 15 radians per second, or in decimal, dividing pi by 15, we get 0.21 radians per second to 2 decimal places. This expression here is termed pi radians, and that's the exact value, and this is the approximation in decimal form. The question doesn't actually ask us to find the frequency, symbol lowercase f, but we could find the frequency because we have the periodic time, and frequency is the reciprocal of periodic time. So 1 divided by the periodic time, 1 divided by 30 in this case, will give us the frequency of 1 upon 30 hertz. In decimals, that would be 0.03334. Don't forget that's a recurring number there. And units is hertz again. Finally, stating the waveform in the form y is equal to a sine of omega t, we find that y is equal to 2 multiplied by the sine of pi t upon 15. Really, pi upon 15 is the omega. Well, that could be written as y is equal to 2 multiplied by sine of 0.21 t. Really, 0.21 is the omega, the 2 decimal places. Note we should have a unit for y, but in this particular example y is not being defined, so we have no units. For reference, if y had been in terms of current, then the units would be amps. If y had been in terms of velocity, then our units of y would be meters per second, etc., etc. Exercise 2b. The sketches below show oscilloscope traces for 2 different waveforms. In each case, we're asked to determine amplitude, capital A, the periodic time, capital T, and the angular frequency, omega. We then have to state the equation of the waveform in the form y is equal to a sine omega t. So if you think you can attempt exercise 2b, part 1 and part 2 without further assistance, I would encourage you to stop the presentation and attempt this exercise. The answers to exercise for part 1 and part 2 waveforms are shown here. The work solutions are shown on the following slides. So here's the solution to exercise 2b, part 1. And we're asked to determine here the amplitude, capital A, of the waveform, the periodic time, capital T, the angular frequency, omega, and then write in the form of y is equal to a sine omega t. So we can clearly see from the sketch of the waveform it oscillates between positive 6 and negative 6, so the amplitude, capital A, is equal to 6 in this case. And by inspection of the graph, we can clearly see that one cycle of the waveform occurs between 0 and 10 to the negative 3 seconds. So the periodic time, capital T, is equal to 0.001 seconds in this case. Don't forget that the instantaneous time, little t, is on the horizontal axis in seconds. We know from the previous slide to calculate the angular frequency, omega, that's simply 2 pi divided by the periodic time, So in this case, it's 2 pi divided by the 0.001, and that evaluates to 2000 multiplied by pi radians per second. So writing in the form now y is equal to a sine omega t, the equation is y is equal to 6 multiplied by the sine of 2000 pi t. I would encourage you to stop the presentation for a moment and think through how we found the values on that slide and how we found the final waveform shown at the bottom. And here's the solution for exercise 2b part 2. Again, we're given a sketch below and we're asked to determine the amplitude, capital A, the periodic time, capital T, and the angular frequency, omega. The solution is shown below, and I will let you work through the solution at your own pace. Just note, in this particular case, the y-axis is actually labelled V for voltage. Horizontal axis is still labelled little t for instantaneous time. Note that one cycle of the sinusoidal waveform occurs through here. So by inspection of the graph, you can find the amplitude, capital A, you can find the periodic time, capital T, in seconds, and you can calculate the angular frequency, omega, in radians per second. And of course, finally state the format of the waveform. In this case, it's V is equal to the amplitude multiplied by the sine of omega t. And of course, the units in this case would be volts. As mentioned previously, there is a separate presentation where we consider equations of the form y is equal to a sine omega t plus or minus alpha, where we solve the problems using analytical methods as opposed to graphical methods. I would encourage you to review that presentation in due course. I will leave you with one problem to undertake. We're given a sketch below as a plot of velocity or speed against time. This is a contextualized problem, so I'll let you read it at your own pace and extract the information appropriately. Again, we have to determine the amplitude, the periodic time, in this problem also the frequency and the angular velocity, omega. Finally, we have to write the equation in the form V is equal to K multiplied by the sine of omega t, where in this case the K is the amplitude. Just be careful with this question. The vertical axis is speed or velocity, V, in meters per second, and the horizontal axis is instantaneous time, little t, in milliseconds. I would encourage you to stop the presentation and attempt problem 1. The answers are shown here in the square brackets. The bibliography used to help generate this presentation, and I hope this has been of use to you. Thank you for viewing.